little demo I'm going to be doing at the end of this talk. So I won't take a ton of time to explain the context of what I'm doing. I'll just tell you that we're doing formal verification of smart contracts, so using the semantics of the EVM that was written by the people at Runtime Verification and the University of Illinois in Urbana-Champaign, which is a complete semantics of the EVM. It passes all of the VM and general state tests, and it has symbolic execution. And so it's really nice to do reachability proofs, which is what we need to do when we do formal verification. But in order to do formal verification, we need to actually verify something. So we need to have some sort of notion of what it is, what properties we're interested in verifying when it comes to smart contracts. And for that, we have developed a tool we at Dapphub called Klab, which does primarily two things. It allows you to specify in a neat format what you actually intend your contracts to do, and then it calls the K-framework prover to verify that this behavior actually is implemented in your contract. And then Klab allows you to step through these proofs, which are basically execution traces with symbolic inputs, and see how things are going, and if they went wrong, what happened. It also does gas analyzing for pretty much all of your contract behavior, so it'll keep things abstract as much as possible. And generate a bunch of specs that you can analyze the gas behavior for your various functions of. So here's the specification format that we call ACT. So we see a simple token contract in like 15 lines here, and we're interested in verifying the transfer function, which just, I think you know what a transfer function does. So here is the behavior implemented, or expressed, I should say, in the ACT language. And the interesting part here happens in the storage location, where we refer to this this storage entry, which is the balances mapping, and we refer to the particular entry from the caller ID, and we give it some abstract value that it begins with, and then say that this value is going to be reduced by minus value. And all of the variables that we see here are real integers. So in order for this to be true, we need to make sure that they actually don't overflow or underflow, which is what we say in this if and only if condition. So from this, we generate a couple of specs. We take the if and only if block, and we generate two specs where we assume the conditions to be true, and one where we assume them to be false. And then if there's an if block present, we assume them in both of these cases. And in the end, we get 3 specs that are relevant to the execution. Here we do a gas analysis of the first time around here. We have like a rough estimate of how the function is going to behave, but we don't refer to the gas in a specific format. So let me show you what this looks like if we have a proof like this. So I pre-run the execution. So let's begin by debugging the passing functionality. So it shows that this execution took 3,000 steps, and these are not 3,000 EVM steps. They're actually slightly smaller, and I'm going to tell you why in just a second. But here you would have an interface that is familiar to you if you've used any debugger, where you can step through. You can have the source map to see what's really going on. And the thing that distinguishes this from any other debugger is that now you have these symbolic values on the stack. And they're going to be constrained in some manner. You can look at what the constraints are and see that they lie within the range of an uint 256. And you can step through to the end of the execution, and you can do a bunch of stuff. So that's kind of cool, but let's look at the fail case, so as I said, we have another spec that takes care of what happens here. And this one is slightly more interesting because it has branching. We can press B to look at the behavior. And now, since this is a fail spec, it's going to end in a bunch of reverts at a bunch of places. So if we go to the case here, this is when the from val is smaller than ABI value, which in this case we should of course revert because we don't have sufficient funds to do the transaction. And we see that if we step through here, we actually end in the revert opcode, which is what we ask for in the fail specs. So that's kind of nice. Let me show you something else. What we also have, if we forget about the behavior for 1 second, is that what we're actually doing here is that we're not only stepping through EVM steps, but we can actually look at all of the things that is being handled internally when we try to execute an opcode. We want to make sure that the stack doesn't overflow, that it doesn't violate whether we're doing a static execution or not, and then we're loading some necessary data, and then we're actually calculating the gas of the opcode, and we're checking whether memory is incremented, then we need to check what particular flavor of the VM we're running, and we do all of these things. So in the end, it takes maybe 7 steps to go through a single opcode. And this is really useful, especially if you have some malformed code or something and you actually run into some stack overflow or some more internal errors of the EVM. Now, this rarely happens with well-compiled code, but if your compiler is broken, for example, this can happen. So I think that's all I'm going to display in the demo. We're working on a bunch of CI right now so that we can automatically take, whenever we've updated the bytecode, we can run it against our specs, make sure that we didn't violate any of the behavior that we have specified. And we're really doing most of the work right now to make sure that our specs are really exhaustive and cover the complete behavior of our smart contracts and make sure that everything that can happen is actually specified in our contracts. There's a couple of fun things that you can do once you have this. You can sort of forget about the implementation and say that the specification is actually what defines your decentralized application, and you can start to optimize for gas. You can rewrite your entire contract in Huff or whatever you want to do. You can have also like a bug bounty on the specs. So you can say like, these specs actually define the behavior of my decentralized application, and if you manage to write an implementation that satisfies the spec but is faulty in some magical sense, then we've screwed up in writing these specifications, and you should get some credit for that. So that was all of the slides that I had. So do I have some time for questions? Nice. I'll take it. Cool.
Questions? You said that the specification could be your application, but can you synthesize solidity from the specification, or do you have to keep maintaining the solidity as you change it?
So in the general case, like you can specify things that you can't reasonably implement, since what you're really doing is like the specification is a little bit like a theorem and the implementation is like a proof. Formal verification is a little bit like Jeopardy, like somebody gives you a question or somebody gives you an answer and you need to ask the question of it. So like, of course, there are things that you can write in the specification that are going to be really hard to find an implementation of. But with most reasonable applications, you would be able to generate an implementation from it, presumably. And this is something that we have thought a lot about doing, and it would be really nice to get out EVM bytecode from the specification language. Thank you.
Any other questions?
Hi there. Sorry, this might be a really silly question. But so from the sounds of it, if you have a if you have a specification for your smart contract that passes tests, then does the kind of the problem move from, how do I put this? There's no way of like systematically evaluating the control flow of your program to determine if the specification is complete, is there? Because I'm guessing that's impossible, right?
Well, it depends on the particular contract that you're evaluating. Like if it's a complete arbitrary piece of code, then of course it's going to be impossible to evaluate. But in the most reasonable cases, we have some fairly finite state machine that we're interested in describing, and then we can actually reach exhaustiveness.
Okay, cool, thanks.
All right, let's bring up our next speaker and thank Martin.
Thank you.
Our next speaker is Aram and not Lucas, but you're next. I guess.
Should I use this? Or?
Yeah. And, yeah. There we go.
Perfect. Good afternoon, everybody. Good to see you here. I think everyone is a bit tired already, but happy to see you. And my name is Aram Jivanyan. I'm cryptography advisor of Zcoin. And we will discuss today Lilantus, a new private transaction protocol that I've been working on during the last few months and which will come to Zcoin networks early 2020. Zcoin is a privacy coin, mostly adopted in the Asian markets, which is using the Zcoin protocol invented by Jan Mears and Matthew Green in 2013. Zcoin uses RSA accumulators and enables users to mint coins of fixed denomination and then spend those coins anonymously, and provides some zero-knowledge proof that the spent coin is valid without revealing its origin. But from the performance point of view, it has some drawbacks. The proof sizes are quite large. They take up to 25 kilobytes. The proof verification can take 300 milliseconds. And the size of the anonymity set should be limited to 10,000 due to practical issues. And it doesn't enable confidential transactions of arbitrary amounts, and still requires some type of trusted setup in order to generate the RSA parameters. Although Zcoin found some smart workaround around this, and it's using the RSA factoring challenge parameters generated in 1991. But with Lilantus, we hope to fix all these functional constraints. It's a new protocol enabling fully confidential and anonymous transactions without requiring a trusted setup, relying solely on standard cryptographic assumptions, and ensuring that the transaction proofs are small, they are less than 2 kilobytes, and the verification is quite fast. We will see the numbers in the diagram. Okay, so just to give high-level insights how it works, it supports two transactions, again enables the users to mint and join split transactions. Mint enables to take as many inputs from the base coin layer as necessary to output new coins, which can hide arbitrary amounts. And the transactions comes with a balance proof, ensuring that the transaction entries sum up, and with range proofs for each output, ensuring that no output coin contains a negative value. And the join split transaction will enable to split, merge, or redeem previously minted coins without revealing their origins. And in order to provide anonymity The main building block used here is the one out of many proofs protocol, which is invented by Jens Groh and Marcus Kohlweis, and which is beautiful enough cryptographic primitive and contains all necessary data to also provide a balanced proof for transactions. This diagram illustrates how the protocol compares with Monero, Zero Cash, and original Zcoin. You can see that we can support high enough anonymity sets of the size of 2 to the power 16 while keeping the proof sizes lower than 2 kilobytes and making sure that the verification that thousands of transactions can be processed in a single block. Yeah, and the motivation behind building Lelantos is simple. We want to provide an alternative solution for private transactions which doesn't require a trusted setup and is solely based on standard cryptographic assumptions, and which in my opinion is also very interesting, is easy to implement and easy to audit. And if you wonder what Lelantos does mean, it is a name of Titan god from Greek mythology who could move unseen without being detected. So find me afterwards if you have any question regarding to the protocol details or...
Yeah, we have time for a couple of questions right now.
Thanks a lot. I wanted to ask, is there a paper peer-reviewed at the conference, or where can I find a paper with the security proof and everything? Thanks.
Not sure if it's peer-reviewed, but it's published already. You can find it at lilantus.io, and we had the chance to discuss it with few cryptographers, including Jens Groh, and Benedict was very helpful also to come up with ideas with modified versions of bulletproofs. But it's not published in any peer-reviewed cryptography conference yet. Thanks.
Hi. Hello. Over there.
Yeah.
Over here, sorry. So, the size, since you said you are using a Sigma protocol, the size of the proof is growing linearly with the number of transactions?
No. The proof size is not growing linearly with the number of transactions. Actually, the proof time and verification times are growing linearly, but the proof size are parameterizable. If you have n transactions and n is 2 to the power 16, then it grows linearly to the exponent value to 16. Thanks.
Yes, my question.
All right. I guess let's thank Aram.
Thank you.
Now we do have our next speaker. Okay, yeah, here. Good. Okay, give a round of applause for Lucas.
Hello, everyone. I'll be talking about a small library that we've been building. Has nothing to do with zero-knowledge proof itself, but hopefully it's something that'll show you how you can use zero-knowledge proofs. Specifically, like how you can deal with large amounts of data that you would need to verify in a proof or need to work with in a proof. If you think of how like most zero-knowledge proofs start out with is like you have some sort of Merkle tree and you need to make a proof about some attribute, a leaf in a tree in Zcash that is like your coins that you have, your commitment. Other in what we're doing, it's sort of data, large sets of data. just a little bit of background information. So we built this at Centrifuge, where we are building a decentralized protocol for companies to interact. So this means they send invoices and purchase orders back and forth. And sort of the very basic protocol is that you have Alice and Bob. They exchange data off-chain. They sign each other's data, and then that data gets committed on-chain. And this is our Merkle root. So when I talk about data, this is described in protobuf. Protobuf is a schema binary format that is developed by Google. They try to build something that was better than JSON or XML to build their APIs with. We're using that as a way to sort of have a very easy, highly efficient serializable data and data structure, and then a way to sort of construct a Merkle tree out of something that looks roughly like this. So what we do is we have, let me skip this. Instead of like using a Merkle tree to prove that a transaction is part of a set, we actually can make a statement about a certain, and in our case, not a transaction. We just talk about documents. So that a field is part of a certain document. So what we do is we take, and this is an example of an invoice. We take each and every field. We create a leaf for each field. We encode the name of the field. So the amount with the value, and the salt, we hash that, and then that's our leaf. So at a later point in time, if you want to use this Merkle root to prove something about your off-chain document, what you do is you say, here's the label, the value, and the salt. You hash that together. You give your Merkle proof, and you can prove that basically this value is included in this set. This now makes it independent of the position in the tree. So instead of having to rely on, give me the 5th leaf in the tree or the 10th leaf, all I need to care about is that the field has the correct prefix. And going back to this specification, so this is something that protobuf is giving us. They use sort of these field tags, so it's just an integer that you describe your field with. So this is basically the prefix we use to encode the field value. So in our case, basically Alice and Bob, they send these documents back and forth. They manipulate them, they validate them. They both know how to encode or create this Merkle tree based on the schema that they have. And can then sign the Merkle root. And if I now have a signed Merkle root, I can give you, like if Alice has a signed Merkle root by Bob, she can make a claim that Bob agreed to, for example, the invoice amount being $1,500. So practical example, let's say I have an invoice that I want to insure, so I want to ensure that my goods will be safely delivered. I don't want to tell the insurance company what I'm selling to my buyer. I don't want to tell them I don't want to reveal any of that on chain. What I can do is I can use these Merkle proofs in a snark. Basically, the insurance provider would give me a snark that has their fee table encoded. I could give my private inputs. So the invoice amount is $1,000. It's the goods are a certain category. The delivery country is the UK, and therefore I should pay 1% insurance fee. I attach a payment to it, and by validating this snark and the payment, the insurance contract can basically say, can check the committed state on chain and say, yes, this was a valid, this is a valid fee that was paid. Therefore, the transaction is now insured. This invoice is now insured. All right. So this concludes sort of the quick introduction to the precise proofs library. It's on GitHub. There's a Go implementation of it. You can sort of play around with it, try to sort of build your own complex trees. So we support all sorts of different data types. You can have sort of just sets, embedded messages, and then just create proofs very easily and actually validate them both in the browser and in Solidity. That's it. Are there any questions?
Any questions?
How can you make sure that it's easy to verify the proofs in different contexts? Like, for example, with snarks, you wouldn't necessarily use the same hash function to build your tree.
Well, if you are doing this within the context of Ethereum, you're ultimately bound by what Ethereum has to offer. The library itself is not opinionated about what hash function you should use. So the one thing you can do is actually you essentially always trust the signature, right? So as Alice and Bob create these trees and sign it, and one thing that we've been thinking of doing to optimize for both snarks and EVM verification, you can have you duplicate the tree once you hash it with Peterson hashes, and once you do it with SHA-256 or SHA-3. And so if you were to make a statement that is public, you can use sort of the SHA-3 branch of the tree, and otherwise you use the Peterson branch of the tree.
All right. Thank you very much.
Thank you.
Next up, we have Marek, and Christopher goes first. Now I made the fuck up.
Thanks. Yeah. If you want to use this thing, up and down is kind of weird.
Do you want to go next? Okay. Test. Cheers. So I'm going to talk about permissionless interchain scaling with IBC, which is not yet in zero knowledge, although it might make use of zero knowledge in the future or allow existing non-zero knowledge blockchains to use zero knowledge features of blockchains which have it. So first, interblockchain has become a bit of a buzzword, so I'll try to specify what we're trying to design here. IBC is a protocol designed to be implemented as part of the state machine of a blockchain. It could be implemented on blockchains which support smart contracts like Ethereum and a smart contract. It could be implemented by custom state machines like some of what we're building with the Cosmos Hub as a module in the state machine or a subcomponent of the state machine. It could be implemented by lots of different future chains, maybe parachains could implement IBC, we hope, if I manage to convince the people sitting in the front row. IBC is designed to be used by heterogeneous chains, so it doesn't require a common virtual machine. We want it to be the case that different chains which specialize in different things, maybe some of those things being zero-knowledge proofs, can implement as part of their state machine, IBC. We want IBC to enable users of a set of chains to choose which chains they trust and how much they trust them. We want it to be permissionless so that different blockchains can open and close connections, relay data, packets, tokens, assets, and code in between each other without anyone other than the users involved needing to approve it, so no governance required. We want it to be in the same vein automatable. Smart contracts should be able to use the interchain system. And we want it to be efficient, at least in the amortized case, such that most of the traffic and transaction throughput should be used by the actual data and the actual state transitions, not the consensus proofs. So the basics of how we do this are that we require an efficiently verifiable consensus transcript, which is commonly known in blockchain parlance as a light client. So in one run in, say, 2 chains with an IBC connection between them. Usually we specify IBC as a protocol in between 2 chains. Each chain will run a like client of the other. It will start out with a root of trust, and it will relay header updates, or some off-chain process will relay header updates from one chain to the other, so that each chain tracks each other's like client and then can verify, say, any state on the other chain with a Merkle path proof. In order for this to be efficient, these headers, so these fragments of the consensus transcript, need to be cheap to verify, and the chains themselves need to have fast finality if you want cross-chain transactions to proceed quickly. You also need a few particulars to be true of the incentive design. So specifically, you need quite strong like client guarantees. You want it to be the case that, since IBC is only running like clients, you want it to be the case that if a like client can be convinced of a committed state that wasn't actually committed, someone gets slashed, because hopefully that will disincentivize validators from lying about the state. So you want stronger guarantees, say, than you might have in a Bitcoin like client. So on top of verification, IBC provides sequencing between 2 chains. If you want to enforce invariance about the combined state of some set of chains, maybe that the balances of a token are conserved, you need to be able to reason about which events occurred in what order on shards of state on different chains. So in order to do this, IBC provides as a protocol TCP-like exactly once message delivery. Each chain implements queues and counters on the messages which prevent replay and only allow them to be committed, assuming the protocol is implemented correctly, in a particular order. So in order to do this, we need Merkle proofs from one chain to the other, which are then verified against the, say, root hash in the header. And those Merkle proofs include the sequence numbers of packets, so each chain can verify that the other chain sent the packets in the order in which it is receiving them and processing them. On top of this, we can build a whole host of different applications. The simplest one is token transfers, where on one chain, maybe the source chain for the token, you have Bitcoin. And then if you want to send Bitcoin using IBC to another chain, you escrow it on the source chain in the IBC handler. You send a packet to the destination chain proving that this Bitcoin has been escrowed. On the destination chain, you can mint, call it a Bitcoin voucher, virtual Bitcoin, send that Bitcoin around on the destination chain, maybe turn it into a user-issued token on the Zcash sampling circuit, send it in zero knowledge, play around with it, even send it to another chain. When you're done, you can burn the voucher and prove that you've burned the voucher to the original source chain, release the Bitcoin from escrow, and now you have your Bitcoin back. So in that sense, it's not like an atomic swap. IBC enables token transfers across chains. IBC can also enable a whole host of different applications, multi-chain smart contracts, where you have different parts of a sort of complex multi-chain state machine executing on different chains, and you pass some part of the smart contract state closure as variables to the next chain in the sequence. You can have delegated security, which we're building out for the Cosmos Hub, where the validator set of one chain, so this is particularly useful for proof of stake, the validator set of one chain agrees to be slashable for equivocations, faults committed on a second chain, which are, if they are committed, submitted over IBC. So that way, say, someone who wants to start up a blockchain but wants to rent out an existing validator set in return for some to-be-determined compensation can convince that validator set to accept slashing risk and so gain the economic security of the original sort of root chain. IBC can also instantiate lots of different sharding protocols, depending on which sorts of ordering guarantees you want, although we think it will be most useful in the case of heterogeneous chains, where different chains can specialize in different application level provisions, but users can use the same assets and can craft complex interdependent state machines across several chains. So, What is the state of affairs? We are trying to write IBC as an open protocol. I want to emphasize that it's not, although it's being primarily developed by Tendermint Cosmos, it is not dependent on the use of necessarily our blockchain or our token. All the specifications are in the open at github.com/cosmos/ICS. And we have a sort of ecosystem working group forming with bi-weekly Zoom calls, which are recorded, and you're welcome to join in person if you like. Let me know. You can find us on Twitter at Cosmos or email me at cwgoes@tendermint.com. We expect MVP implementation along with a MVP final specification sometime in summer 2019. Don't want to be too specific. Thanks. Questions?
Hey, thanks for the presentation. So I'm still slightly confused. If you send Bitcoin in an escrow and then prove it onto one of the Cosmos chains, how do you use the information of the burned token to release the Bitcoin inside the Bitcoin network itself?
How to use the information of the burned token. So on the Cosmos chain, you mint a Bitcoin voucher, right? And that Bitcoin voucher is stored in some key in state, which the source chain knows about. The Bitcoin chain knows about that key in state and can read the amount of that voucher. So then when that voucher is burned, you can send a packet back to the source chain, which proves that the amount decreased, and the source chain will, and the packet also contains data about which address the original Bitcoin should be released to, then the source chain can accept that transaction. So the Bitcoin, to be clear, the Bitcoin chain would need to change its state machine to do this. We have another more complex solution to work with the existing Bitcoin chain using like a multi-party ECDSA peg. But two custom chains can need to understand part of each other's state machine, and then they can do this safely.
Could you say something a bit more about the scalability of the protocol? Because I can see that when it's like one-to-one communication between two blockchains, I see it working. But in the future, if there is many communication or many sidechains or blockchains communicating to one to each other, this means like a lot of miracle proofs will need to be proved and so on. So yeah, do you have a solution for that? Or?
That's a good question. I mean, IBC is designed to, it's not specific to a particular network topology, and we expect the network topologies that emerge to be reflective of the economic properties of the commerce that the chains are trying to provide. So for example, if there were a bunch of payment chains around the world, most commerce is local. Most payments in Shanghai are to other vendors in Shanghai. Most payments in Oregon are to other vendors in Oregon. Occasionally those two chains need to settle, Shanghai-Oregon transactions, but that's much rarer. So we would expect the payment chains to be local or maybe to be only one hop away via IBC in most cases, and in the exceptional cases, yes, the payments are slightly more expensive.
All right, let's thank Christopher again. Now we do have you guys. Next up is Marek and Anna to talk about the Parity Zcash implementation, or Parity and Zcash Foundation implementation.
Thanks. Yeah, exactly. So we are here to give you like quick overview and like what is happening right now regarding Zcash and the Zcash implementation that's on the road. So there is right now in development, a Zcash Rust implementation done by Parity here in Berlin. Like not actually here in Berlin, but located here in Berlin. So last autumn, Parity and the Zcash Foundation partnered to give an implementation in Rust. This is a fork of the Parity Bitcoin code, and we're using the Rust cryptographic libraries from the Electric Coin company, so before the Zcash company.
All right, so maybe I'll
tell a bit about the goals. So currently, Zcash, there's a single implementation of Zcash protocol, and as many of you know, if the implementation if there's just a single implementation, basically the specification of the protocol very often reflects all the bugs that may be like in this implementation. It was the case for Bitcoin, so there are like many bugs in their interpreter or other parts of the code base that other implementations of Bitcoin had to replicate in the future. Basically, this new implementation will give like Zcash Foundation, Zcash ecosystem, something that Ethereum had from day one. So basically, it will separate implementation from a specification. So we'll have multiple clients. This is the second point, like prevent implementing specific bugs. We base our Zcash implementation on top of Parity Bitcoin code base. So Parity Bitcoin, it's not well-known project. So at Parity, there was like a group of Chinese miners that reached out to us like in, I think, 2016, who asked us to implement like an independent node implementation, Bitcoin node implementation from scratch, and we did that in 2016 and early 2017, but since then this implementation hasn't got much traction. It was used by several smaller projects, and we only implemented the features that were required like by those projects, but it's not a like fully featured, well-optimized implementation. But right now we are hoping that with the Zcash implementation, we could actually, with the Zcash fork, we can actually take this implementation to the next level, so implement many optimizations in which and both Bitcoin implementation and the Zcash implementation will benefit from those optimizations that we'll implement for Zcash. And the last point is a possibility for Polkadot with Zcash Bridge. So basically, at Parity, like our priority number one right now is Substrate, which is the framework for building blockchains, and Polkadot, which is a project to connect those blockchains together. And eventually, we'd like to also build a bridge between Zcash client and Polkadot client. So this implementation will be just the most critical part of this project. Yeah.
And I think in general, this quote from Josh from the foundation actually captures it quite well, who said that an independent node implementation provides more options for the Zcash miners and users, which promotes healthy decentralization of the cryptocurrency protocol as it matures. And this is exactly what the Zcash Foundation wants from this implementation. We just want the Zcash community to grow and have different options, and not only one. So where can we find this implementation? It's on GitHub, and you can have a look and build it and run a node if you're interested. Right now, what we're doing is, it's still in development progress, but we're good. We're optimizing and testing. So if you want to run and like find some cool warnings or anything, let us know. And we can also give you an overview. So what we still are doing is we're benchmarking and we're testing, optimizing, seeing how things are going. The other thing is always documentation is always nice. We're not there yet. And of course, that's why we are telling you about this. We want people to like use it for now, like for test reasons, and also like for you to spread the word.
Yeah, I think this code base is also very good for Rust beginners because it's relatively small compared to other like crypto projects, mostly because of lack of those features that we just haven't implemented yet. So there's like the RPC is just very basic, and like there's not that many optimizations. So if you just want to get some hands-on on Rust, like I think it's a good repo to look at. And if you don't understand something, just create an issue on GitHub, and there'll be someone answering it and helping you out.
So that's it from us. And if you want to contribute, here's the repo again. Contact us on Twitter as well if you have any questions. And yeah, we'll take questions if you want, if we have time for that.
Is it reference compliant yet? Can it sync like to the head of Zcash chain?
Sorry?
Is it reference compliant yet with the reference node?
Yeah. So yeah, we are importing the Zcashd database. That should be working, and yeah, so you can check it out and syncing and everything.
Yeah, so there are like two options. So, I mean, there were two options with the Parity Bitcoin client. So you can either sync the chain, or you can basically import like the existing Zcashd database. So I actually don't remember, like, so we had like an open issue for importing the database because we did it for Bitcoin, but oh, is it, okay, it's working as well here. Ready, so.
Any other questions?
So, and if you want to run it, by the way, yeah, you can run the release version because the debugging version will take a little longer.
Do you plan to expand with respect to the original specification of the protocol?
Right now, not. So we are right now focusing on like sapling and sprout specifications. Of course, if like Blossom is going to come up, I think this will come like, of course, in our like timeline. But for now, we are like optimizing the code that we have for sapling. Yeah, sure.
So I think that in future it's possible to do something that we have, for example, with Parity Ethereum client. So basically have a set of command line options that allows you to kind of load some specific chain or some specific options. So in Parity Ethereum, we currently support, I don't know, like by default 15 different cryptocurrencies, and some of those cryptocurrencies have, I don't know, like slightly modified state transition mechanism. There's I don't know, some new opcode enabled and stuff like that. So I think it's possible to also make this kind of modifications to Zcash implementation in future, and allow you to experiment with the code base, with the protocol, and maybe possibly submit some like improvement protocol proposal to the Zcash Foundation.
Yeah, I was specifically thinking about the Rust implementation of bulletproofs, since it's the best one in performance. So I was thinking that maybe you were thinking about it.
I mean, as far as I know, not.
Yeah. So as far as I know, not now. Yeah. Like this is not on the.
It's worth to be said that the Zcash crypto, like all the sapling stuff, is also implemented in Rust. So all of their stuff is also already in Rust. It's just wrapped around a bunch of C++. And yeah, like having some insight into working on this, part of the goal is to give more power to the Zcash Foundation over the Electric Coin Company, and therefore like start having a conversation of which improvements are possible and start collaborating in a slightly more decentralized fashion.
Thanks for saying that, Fred. Yeah, absolutely.
All right. Let's thank Anna and Marek again.
Thank you.
Are you there? Yeah. Cool. Okay. I didn't know if you guys were here. Okay, so that actually concludes the lightning talks, per se. We have one more short presentation, which is basically this morning, I don't know if you guys remember, there was a workshop, which was like a use case deep dive workshop. And so, Anna, are you coming back on stage? Okay, cool. So Anna's back. We're going to hear a little bit about what happened in that workshop and some of the results that you guys have. Cool. Welcome. So maybe just introduce yourselves too. Sorry.
Thanks. Do you want to go first?
You go first because you're the workshop goal.
Okay, I'll quickly just say I'm Liz Steiniger from Least Authority.
I'm Tanya from Least Authority.
Yeah, and I was here before. I'm Anna from the Zcash Foundation. Hi.
Oh, okay. So we did as Anna mentioned, we did a workshop earlier today about ZK proofs in real world. I think. Yeah. Okay, yeah, I'm supposed to talk about this. So our workshop goal, we wanted to talk a little bit more about how to take the ideas, the theories, the practices of the math and everything of zero knowledge proofs, and how to actually apply those into real world circumstances where privacy is an issue. And we wanted to get the different groups that are involved in that kind of like pipeline of how things get out to the real end users, get those different people involved together, and talking a little bit more about these cases, because we do feel that there's just a bigger need for knowledge sharing. This was something Anna and I have been talking about for a long time, and Tanya joined us on this effort too, that yeah, it's important to get these ideas from theory into practice. And so we thought that by having people get together and talk about some actual use cases, that this would just help everybody's brains get exercised on this and perhaps inspire some, follow-up stuff. Do you want to say anything about that?
So just to give you a general sense of the workshop, what we decided to do is we decided to keep it small, about 20 people. And we had like a rough outline of use cases, but we mostly discussed it with the group, and that we fine-tuned those use cases. And we thought it would be a cool structure to divide up into about like 4 groups, everybody discuss separately, and then come back together and present like whatever outcomes you could actually create in 30 minutes. So, but the goal of this workshop, also to like iterate on what Liz is saying, is this is our first workshop of this sort, and we want to do more like that. So the call to action is, if you have any topics, us at Lease Authority and Anna Kaplan as well, we'd love to see like a longer form version of this. So this being the first iteration of that, I think it did pretty well. And we don't want to take up too much time of this. Anna's going to tell us about the use cases, and then one of the groups is going to present their concept.
So yeah, when we did the workshop today morning, we wanted the participants to actually like find their own use case, because we didn't want to make them talk about something. So actually, as we also thought, people came up with tons of cool ideas, and we thought it's worth sharing. So of course, finance and accounting, and specifically auditing, actually was one of the first topics that came up. And somebody said it's a very boring topic, but we should tackle it. And yeah, that's true. We should tackle it, even though it might be boring sense. The second thing was a very Berlin-specific thing as well, or a Berlin-specific thing maybe, and for a lot of different cities as well. Applying for a flat is super annoying. So the idea of the participants was to find an anonymous way to actually say you have enough money to actually get the flat. The third idea was a proof of age for buying something online or any other kind of need where you would want to prove your age. Fourth idea was a passport control at the airport. There we had some difficulties, thinking, okay, we have to include the government and so on, and how to do that. The fifth idea that was discussed for the use cases was a proof of humanness, because this is still not that perfect right now. So there was a tie in the end between the fifth and the sixth option, and the sixth option was actually voting systems, how should we vote? And when we voted actually on the use cases, there was a tie, but the participants decided to talk about voting systems. We built 4 groups, and one group came up with something super interesting, and they're going to present it. So I'm giving over to Tim, and yeah.
Thanks a lot for organizing the workshop. I actually did not plan to support Lightning Talk today, but after seeing what another group, not the one I was in, came up with, I really felt that this is something we should share here and hopefully also validate in a proof of concept. So usually we would say it's a paradoxon that you actually bring it together, that you vote anonymously and that you get provable correctness. The group which was presenting a tangible, actionable result was the group Joe was in as well, with Matt Stevens, Antonia, Napa, and Eckert Bockwedel. I helped with the presentation. So without further ado, Joe, please come up and walk us through the solution you engineered in that very short time frame. And I hope that we can find some supporters after that short pitch to actually make a proof of concept for it.
Yeah, hello, I'm Joe. So yeah, we just started out with like the assumption that like one person gets one vote, and that we have some sort of system for mapping a unique digital identity to one person, and actually just giving a person one vote, and that like a token would basically represent the vote, and so you could send out like one token to everybody, and they could send these tokens to some address that represents an option in the vote, and then you can say like this wasn't tampered with in any way. So the objectives are voting is anonymous, so nobody knows who you voted for, and they can't really bribe you to vote in some way because they could never verify that you actually voted that way. And then that the outcome of the election is verifiable, so that would be like if a state gives you like two options for candidates, that they don't like just give 1,000 votes automatically to one candidate before the election even starts. So you should be able to publicly verify that. And then some of the components we used basically like, we assume that we have a Zcash like system to host our tokens. I think you could actually do this with a nonce-based like accounts system also. But yeah, you need like some sort of like nonce or transaction in a chain and a mempool, and then private addresses and transactions for the anonymity, and also like a view key for addresses, one like to verify the outcome of the election, so that like the government could say like, hey, these are the view keys of all the options, so you can actually see it. And also like if you are eligible to vote and nobody sends you a token, you could show your address and say like, look, nobody gave me a token to vote with. Yeah, that was my little sketch of how TXOs work. But yeah, so basically like the process would be that you actually cast your vote before you receive your voting token. So if you have like a parent and a child, normally in like Bitcoin or Zcash, if you submit like a child transaction, it'll just sit in the mempool. It's not a valid transaction yet until its parent comes in, and then all of a sudden it's a valid transaction and it goes through. So in order, like, our main motivation here was to prevent bribery, so that like I get my voting token and I don't just sell it to you for you to vote with. So you actually like cast your vote and it just sits in the mempool. And then after some deadline passes, like the voting deadline, all of the tokens are issued, and then it's just like all of the children are populated with their parents and they all go through. And then like these tokens would basically have a hash time lock contract with them. And so like if you had like two candidates or two options in your vote, there'd kind of like by default be a third candidate called abstain. And so like if you just never submit a transaction to the mempool to cast your vote, it just, yeah, in this HTLC, it just automatically goes to abstain. And the point of this is to add up all the votes at the end. So like the sum of the votes that the candidates have should equal the total number of people that are eligible to vote. So yeah, this, you can avoid the like, oh, there were 1,000 tokens like automatically voted for this person. And then, yeah, so you add them all up, and then there's like an abstinence option, and then like, yeah, the problem would be like if you kind of just make a child transaction, if like you buy my vote and I can just like send you a child transaction, and then you make like a grandchild transaction to vote. Yeah, we want to prevent that, so that's like the only thing we didn't get to. But I think you could, either limit like how far down from the token issuance transaction it can go, or if you use like a nonce-based chain, you can say like, yeah, tokens are issued at a nonce of 1, and anything with a nonce of 3 or greater just automatically goes into like a cheater category. Yeah, so that's just what I thought of this morning. So there you go.
Can you stay for a moment?
Yeah, sure.
Hey guys, I just want to ask how many people of you know UTXOs? Just hands up. Hands up? Oh, that's great. Okay, then we don't need to explain it. It's wonderful. So, yeah, follow up. If you think that this is an interesting approach, I think it would be super interesting if we could find a way to just do a test implementation. I don't know how available you are for this, but maybe this also helps just to have the structure to try it out. So if there's anybody who wants to support some proof of concepts here, please speak to me, and hopefully we find a way to coordinate it. Thanks.
Do you want to say anything else? Yeah, first I just want to say thanks to all the participants who also were in the workshop. And it's awesome that this happened, and I think like 30 minutes of group activity. So yeah, are we supposed to do questions?
We can do questions. Any questions? Not really. All right, let's not do questions.
That's okay. Thank you again for the workshop.
Yeah, thank you very much.
So now we have another break, actually. We have about half an hour. And then, I'll go back up here, I'm short. And then after the break, so like at 5, we have something in here that we've been doing every time we do the Zero Knowledge Summit, which is called the Park Bench Panel. You may or may not know what that is. I'll describe very quickly. There's a few people on stage